Events like the eruption of Mount St. Helens in 1980. I've been combing through the archives and I came across a special newscast from the day of the eruption. It happened on a Sunday, May 18th. An earthquake hit a little after 8:30 in the morning. That caused the north face of Mount St. Helens to slide away, making possible an unholy explosion of hot lava, rock, and ash.
The eruption of Mount St. Helens has once again seized the attention of geologists and the global public alike. This recent event, occurring with astonishing ferocity, shocked even those most familiar with the Pacific Northwest's volatile volcanic past. For decades, Mount St. Helens has stood as a symbol of geological unpredictability, and its latest eruption proved no less formidable. Billowing ash columns soared high into the atmosphere, the skies darkened over swaths of Washington state, and the air rumbled with the force of nature's upheaval. The eruption, though sudden in its final burst, came after weeks of low-level tremors and subtle seismic fluctuations, which many experts initially dismissed as inconclusive. But when the mountain cracked open with a renewed violence, the world was reminded once more of its latent fury. Before we start, smash the like and subscribe buttons for more updates. At the heart of the geological tension lies the intricate dance of tectonic plates beneath the Pacific Northwest. Mount St. Helens is part of the Cascade Range, a segment of the volatile ring of fire that encircles the Pacific Ocean. These volcanic systems are fueled by the slow, grinding subduction of the Juan de Fuca Plate beneath the North American Plate. While the Cascade Range hosts several potentially active volcanoes, Mount St. Helens is among the most watched due to its dramatic 1980 eruption, which redefined modern volcano monitoring practices. The most recent eruption, however, brought a new twist, as lava surged from the crater and pyroclastic flows barreled down its flanks. Instruments across the continent began to stir, notably those buried beneath the thick crust of Yellowstone. The Yellowstone Caldera, often referred to as a supervolcano due to the sheer scale of its eruptions in prehistoric times, sits hundreds of miles east of Mount St. Helens. Yet, within minutes of the eruption, sensors embedded deep within the Yellowstone system began transmitting a flurry of data. Earthquake monitors, GPS units, and gas emission sensors lit up with activity, triggering Yellowstone's alert systems for the first time in years. Although no eruption followed at Yellowstone, the sheer responsiveness of its system in the wake of Mount St. Helens' eruption stunned the scientific community. The trigger wasn't a mechanical failure or misinterpretation of data. It was a real measurable shift. Seismic waves generated by the eruption traveled underground, interacting with the deep and complex magma plumbing that snakes through the Earth's crust all the way to Yellowstone's dormant heart. The possibility that Mount St. Helens' eruption could exert such influence over Yellowstone's geological system has reignited fierce debate. For decades, researchers have speculated about the deep interconnectivity of North America's volcanic networks. While it's widely accepted that most volcanoes act independently, the idea of seismic or magmatic domino effects, where one event stirs another, has remained controversial. But the instant synchronous response of Yellowstone's alert system in the aftermath of Mount St. Helens' eruption demands attention. GPS sensors in Yellowstone recorded ground uplift and horizontal motion, subtle but significant. Gas emissions in certain areas ticked upward, especially carbon dioxide and sulfur compounds often associated with magmatic movement. Microquakes began rattling the region, tiny tremors that normally go unnoticed but in this context paint a worrisome picture. It's crucial to understand that what's occurring is not a chain reaction in the traditional cinematic sense. Yellowstone did not erupt, but the underground shifts indicate that pressures, otherwise stable or dormant, were nudged into motion. The vast magma chambers beneath Yellowstone are still considered to be in a cooling phase, and scientists have maintained that any future eruption is likely centuries away. However, this event underscores the point that these systems are not as isolated as once believed. Geological time moves differently, and even subtle interactions across regions can set off ripples with long-term consequences. The real drama, then, lies not in fire and ash spewing from Yellowstone's mouth, but in the invisible subterranean changes now underway. Adding to the mystery is the emerging data from a network of deep Earth monitoring stations stretching from the Cascades through the Rocky Mountains to the Yellowstone Plateau. These stations are equipped with advanced instruments capable of detecting ground deformation at incredible depths. In the hours following the Mount St. Helens eruption, several of these stations picked up strange low-frequency tremors, sometimes referred to as deep, long-period events. These signals often suggest movement of magma deep underground, too deep to cause immediate eruptions, but significant in terms of geological dynamics. What made these tremors exceptional was their reach. They weren't isolated to Washington State or even Idaho. The pattern traced an arc extending through Oregon and into northwestern Wyoming, suggesting a broader mantle-level response. This isn't just academic curiosity. The data have real implications for risk forecasting, disaster preparedness, and long-term planning for communities scattered across the western United States. The implications reach beyond seismology and into politics, economics, and ecology. Federal and state authorities have already mobilized resources to assess infrastructure vulnerabilities, from power grids to transportation networks, especially along the Interstate 90 corridor that links many of these geologically active zones. The Department of the Interior has confirmed that a special task force will be assigned to investigate the implications of the Mount St. Helens event on broader volcanic systems, including but not limited to Yellowstone. What truly elevates this incident to a new level of urgency is the reaction of the Yellowstone Volcano Observatory YVO, which raised its alert level from green to yellow in the wake of the event. This doesn't mean an eruption is imminent, but it does indicate heightened monitoring and concern. Scientists at YVO and the USGS are now recalibrating their models, using the fresh data from Mount St. Helens to reassess the stability of magma bodies beneath Yellowstone. The recalibrations aren't trivial. New variables have been introduced into the equation: rate of seismic wave transmission across regions, response time of magma reservoirs, and atmospheric pressure shifts following an eruption of St. Helens magnitude. Further complicating the scenario is the psychological and cultural weight that Yellowstone carries. Unlike Mount St. Helens, which has erupted several times in the last few centuries, Yellowstone evokes a more primal fear. Its supervolcano status lends it an almost mythical quality, a ticking time bomb buried beneath one of the most visited national parks in the United States. This association has led to sensational speculation in the past, with doomsday theories often outpacing scientific discourse. But this time, scientists themselves are urging caution, not panic, while not dismissing the relevance of the latest chain of events. They acknowledge the need for greater understanding, not only of Yellowstone's unique system, but of the ways these geological giants might communicate beneath our feet. Public interest has surged, and with it, funding for research. Multiple academic institutions are now collaborating on urgent studies to map the deeper crustal structures connecting the Pacific Northwest with the Intermountain West. One of the most intriguing areas of study is a vast, slow-moving plume of superheated rock that may stretch from Northern California up to Wyoming. This mantle plume could act as a kind of pressure valve or conduit between different volcanic systems. Its existence was debated for years, but mounting evidence and the recent eruption have lent credibility to the theory. If true, this plume might be the invisible thread connecting the drama of Mount St. Helens to the rumblings beneath Yellowstone. Even from a global standpoint, the event holds significance. International observatories and space agencies have turned their satellites toward North America, scanning for thermal anomalies, ash dispersion, and atmospheric gas shifts. Climate researchers are also watching closely. While Mount St. Helens' recent eruption was smaller than its 1980 counterpart, it still injected significant ash and aerosols into the upper atmosphere. This has implications for weather patterns, particularly across the northern hemisphere. If even minor eruptions can affect local climate conditions, what might a region-wide tectonic shift entail? All of this has brought a renewed focus on preparedness. Across Montana, Idaho, and Wyoming, emergency management agencies are conducting scenario drills and updating evacuation protocols. Not in response to an imminent eruption, but as a precautionary step in light of the evolving geological landscape. Schools are participating in earthquake drills. Hospitals are stockpiling supplies, and national park authorities are refining their communication plans to handle a potential surge in concern from the public. Even as calm returns to the forests and valleys around Mount St. Helens, the undercurrent of urgency has not subsided. Beneath the surface of these preparations lies a deeper philosophical question. one that has always accompanied the study of volcanoes and earthquakes. How well can we truly understand the planet we live on? The Mount St. Helens eruption and its unexpected ripple effects across Yellowstone have once again underscored the humility required in the face of Earth's immense power. The sensors, satellites, and supercomputers we rely on still cannot predict every movement with certainty. What we have gained, however, is a greater appreciation of the complexity of these interconnected systems. As geologists pore over petabytes of data and volcanologists recalibrate their models, there's a growing sense that we may be standing at the cusp of a new chapter in Earth sciences. The Mount St. Helens eruption didn't just release pressure from a restless mountain, it cracked open new questions about the fabric of the North American continent. It offered a glimpse into subterranean dialogues that span states and shake the foundations of what we think we know. And most of all, it reminded everyone that our planet is very much alive, always shifting, always speaking, if only we know how to listen. The eruption of Mount St. Helens and the unexpected activation of Yellowstone's alert systems have ignited a new chapter in understanding the hidden dynamism beneath the western United States. What makes this moment so pivotal isn't just the geological violence on display, it's the doorway it has opened into an era of increasingly sophisticated volcanic science, where subtle interconnections are starting to replace the long-standing belief that these systems act in isolation. Mount St. Helens, though already well monitored, displayed a type of behavior in this recent eruption that diverged from earlier patterns. The magma that burst forth was chemically different from what was sampled in previous decades. Geochemical analysis from airborne and ground-based collection teams revealed signs of a deeper origin, suggesting that the magma source for this eruption may have come from lower in the Earth's mantle than usual. This points toward either a reactivation of long-dormant feeder channels or even an entirely new pathway being forged through the crust, both of which have major implications for volcanic forecasting. The presence of high-pressure, gas-rich magma also indicates that volatile accumulation had been quietly occurring for a much longer period than anyone had assumed, hidden behind minor seismic rumblings that never crossed alert thresholds. Meanwhile, Yellowstone's response has given scientists their clearest modern example of a system reacting, not erupting but responding in real time to an event hundreds of miles away. It presents a compelling case for the concept of passive triggering, a scenario in which powerful seismic waves from one event can disturb or awaken sensitive zones in another. These are not aftershocks, nor are they direct threats, but rather indications of stored energy being redistributed. In Yellowstone's case, this redistribution showed up as swelling in the Norris Geyser Basin, an area known for hosting the park's most active thermal features. While geysers like Steamboat and Echinus are inherently unpredictable, a noticeable uptick in both frequency and intensity of eruptions was recorded just days after Mount St. Helens erupted. More telling was the increase in ground temperature across certain geothermal zones, readings that were consistent across multiple sensors, independent of solar variation or weather changes. In the backdrop of this sudden awakening lies a deeper concern: the unknowns that persist in mapping volcanic plumbing systems. Though satellites, drones, and deep Earth tomography have vastly improved our imaging capabilities, scientists still struggle to pinpoint the full size, shape, and behavior of the vast magma reservoirs below Yellowstone. It's not just about volume. It's about pressure gradients, fluid pathways, and mineral content, each of which alters how energy moves and accumulates. The recent eruption has pushed agencies like the USGS to fund newer, more sensitive geophysical instruments. These tools are being deployed in a more densely packed array throughout the Intermountain West, creating a real-time 3D model that updates every few minutes. This live map of geological strain and deformation could someday provide early warnings not just of eruptions, but of shifts in subsurface conditions that could lead to cascading environmental effects. Cascading effects, in fact, have become a central focus. The Mount St. Helens eruption, though localized in terms of lava and ashfall, had broader atmospheric consequences. Jet stream disruptions were recorded as high-altitude ash plumes interfered with west-to-east wind patterns. This led to delayed flights, turbulent conditions over the Midwest, and even temperature drops in parts of the northern Great Plains. Volcanic ash has a peculiar way of interacting with the climate. It reflects sunlight, temporarily cooling regions under its path. That effect was noted across parts of Montana and South Dakota, where slight but measurable reductions in temperature and solar radiation were observed within 2 days of the eruption. If eruptions like this one become more frequent, or if another large-scale event occurs, the accumulative impact on weather systems, agriculture, and air quality could become more pronounced. Back on the ground, ecological systems began responding in subtle but significant ways. Wildlife within Mount St. Helens National Volcanic Monument scattered quickly after the eruption. Trail cameras and tagged animals indicated mass movements of elk herds, deer, and even smaller species like marmots and foxes. Interestingly, similar migration shifts were noted near Yellowstone within a week of the event. Elk and bison patterns deviated from their usual summer routes, choosing higher ground and less trafficked valleys, a behavior that has previously been recorded in advance of large earthquakes and geothermal disturbances. Some scientists theorize that these species can detect magnetic or geochemical shifts undetectable to human instruments. Others suggest that the animals are responding to low-frequency sound waves, inaudible to us but acutely disturbing to wildlife. These behavioral shifts have drawn the attention of ecologists who now see wildlife tracking as a supplemental early warning tool. By combining animal movement data with geological monitoring, researchers hope to build predictive models that account for natural biological sensitivity. This multidisciplinary approach marks a new frontier, one where volcanology meets ecology, and data from both realms are treated as mutually informative rather than isolated silos. Universities in Montana and Washington are launching joint programs to study the long-term effects of volcanic triggers on wildlife corridors, migration routes, and biodiversity resilience. As focus sharpens on Yellowstone's reaction, it's also critical to understand the psychological landscape reshaped by these events. For decades, Yellowstone has occupied a unique space in the public consciousness, a place of wonder tinged with a whisper of dread. Books, documentaries, and viral internet posts have long speculated about its potential to trigger a planetary catastrophe. And while most of that rhetoric is exaggerated, the scientific basis for concern is real. This is a caldera capable of eruptions that could darken skies globally and rewrite human history. What makes this moment different is that for the first time in decades, that theoretical risk moved ever so slightly into a more tangible zone of uncertainty. Public interest has surged in response. Downloads of USGS volcano monitoring apps have spiked, as have enrollments in online geology courses. Visitors to Yellowstone National Park have increased, not deterred but rather drawn by curiosity and a desire to witness Earth's tension points firsthand. Park rangers report a rise in questions about hot springs, mud pots, and geysers. Visitors want to understand what they're seeing. Some are reassured by the stable beauty of the landscape. Others are unsettled by every tremor. There's a growing tension between awe and anxiety, a duality that park staff are now trained to address with empathy and science-backed facts. The financial and policy ripple effects are beginning to take shape as well. Insurance companies are reevaluating risk assessments for properties in western volcanic zones. Infrastructure projects are under review, particularly those involving pipelines, water reservoirs, and power lines that traverse seismically sensitive areas. The Mount St. Helens event has placed stress testing for volcanic impact back on the legislative agenda. Senators from affected states are now lobbying for updated federal funding to improve both research and readiness. These aren't theoretical discussions anymore. The evidence of systemic sensitivity has moved it into the domain of actionable policy. What further complicates matters is the role of groundwater systems beneath both Mount St. Helens and Yellowstone. The movement of magma doesn't only cause eruptions, it can also superheat aquifers, destabilize faults, and trigger phreatic steam-driven explosions. In the aftermath of this eruption, new hydrothermal features have emerged at Mount St. Helens. Small steam vents and boiling ponds appeared where none existed weeks before. Ground-penetrating radar has detected the upward movement of superheated fluids, a phenomenon that bears close watching. In Yellowstone, subtle shifts in water chemistry are now under analysis. Small changes in pH, mineral content, and temperature, insignificant in isolation, could be indicators of deep underground heating. What this all points to is a need to reframe how interconnected systems are viewed. not just in geosciences, but in policy, education, and public engagement. The Mount St. Helens eruption didn't just awaken a mountain, it disrupted assumptions. It illustrated that in an age of precision instruments and high-speed data, nature can still surprise. It made clear that we are participants in a living system, not just observers of static geology. The Earth breathes, pulses, and shudders beneath us in ways we are only beginning to comprehend. And so the work continues. Scientists will dig into layers of ash, scrutinize seismic logs, model subsurface thermodynamics, and adjust their understanding of what's possible. Each data point tells part of a story still unfolding. Mount St. Helens roared back to life not just as a geological force, but as a messenger, perhaps even a catalyst, reminding us that Yellowstone and the greater interior West are not sleeping giants, but complex, responsive, and deeply alive systems. The land beneath our feet, though ancient, is never truly at rest. It listens, it echoes, and when it speaks, it changes everything. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us. What are your thoughts on Mount St. Helens triggering Yellowstone alert systems? We want to hear from you. Thank you for watching, and see you next time.